Okay, so as per the protocols, we need to introduce ourselves every time. And uh, this is, I guess, my fourth or fifth course with the National Programs on Technology Enhanced Learning portal, which is a centrally managed portal by MHRD. And it's managed by IIT Madras. So I'm Shazam Bhatt, and I'm a PG student at IIT Bombay and a DAD student at TU Berlin and Paul Rudd Institute. So this course is being offered by Professor Pradeep Kumar from IIT Kanpur, I believe, and the course is Electromagnetics in Guided and Wireless Media. And I wish to turn on my camera, but the problem is that Google Meet doesn't allow to turn the camera and share the screen simultaneously. So we may need to just keep the camera off. Anyways, what we are going to basically do in this session is to recap whatever has been taught in this particular week uh, in this course, and it will be a brief, or rather, I should say, quick recap of whatever has been covered, and I'll try to go over the things, including the applications. That will be mostly my concern because I guess the professor does a very good job in explaining the things from the basic, I should say, concepts. So I'm not going again to those particular things which you can learn from the videos uploaded on the NPTEL portal. Rather, what I should do is that I should make you aware about the applications which are basically being looked into this particular, I should say, field. So why are we studying electromagnetic waves in guided and wireless media? So if we talk about the course introduction, what is basically being taught in this course, it is the electromagnetic waves in both wired and wireless media. So this can be microwaves, this can be radio frequency waves, and basically, we are dealing with the electromagnetic wave propagation in transmission lines as well as it can be in the wireless media. And the prerequisites, if we see, they are the vector analysis and the vector calculus. So electrostatics, magnetostatics. So you should be having at least a basic understanding and knowledge of the Maxwell's equations, electrostatics, charges, electric fields, magnetic fields, vectors, vector calculus, gradient divergence, curls. So that is basically required in this course. That's why you see that the vector analysis is at the top, followed by electrostatics and magnetostatics, because these govern the basically the dynamics of the electric and the magnetic field in the electromagnetic wave. And as such, you should be having the knowledge of what basically a gradient is, what basically a divergence is, and what basically the curl is. So these three things you should be knowing. You should be knowing about certain theorems, Green's theorem, the Stokes theorem, how to go back and forth from a surface integral to a volume integral, what basically the surface integrals and the volume integrals denote, what are basically those integrals. That's why these things are basically covered in the first year of the I should say undergraduate program. The reason is because they are prerequisites of all of those courses which are built after the first year undergraduate courses. And then electrostatics, you have been studying from class 12th, I guess, class 10 plus 2. You have been studying about electrostatics, about the electrons, about its behavior, charges, insight about I should say, how does an electron behave in an electric field? How does the charges behave on different structures, whether it's cylindrical, spherical, conical? You have been solving a lot of problems, particularly in someone if someone among you has been aware about the certain entrance examinations. They are mostly, I should say, uh, give the problems based on these electrostatics and as well as magnetostatics. And let me just, what is this? Admit. So I should change the settings first so that it can admit the anyone automatically. Just give me a moment so that I can change the settings here. I should be able to do it. So settings, host controls, host management, it's not here. You okay? So let it be. Maybe you can just do it later on. So these are the prerequisites which even the professor might have told you to. This is annoying. I just want to admit the guests automatically so that I don't have to add people every time. Where can I do it? Just give me a moment. Meeting details. Let's restrict you. Host must join. Yes, I'll do it this thing. Okay, so it's done. Anyone can join the meeting freely and they don't need the permission. So, so this is the outline of this course basically, and I don't know about this industry support thing, so I'm going to leave it there. Maybe professor, you can just contact the professor directly or the NPTEL support team about what this industry support is exactly about. If you guys are going to have some applications in certain defense sectors where these electromagnetic waves and electromagnetics are is being used in the real world application. So the course layout is basically, first of all, this is an elective type course as per the NPTEL guidelines, and this is an undergraduate or a postgraduate course. It can be it's mostly I should say, first year, maybe postgraduate. I don't know exactly if it is taught in the postgraduate course because it's mostly an undergraduate course. And during the later stage of the undergraduate course rather, and the course outline is the course layout is exactly like this, which is being taken from the NPTEL portal. So the essential thing is that the the essential thing here is that these topics will be covered, but this is just a rough outline. These may include certain other topics, subtopics rather, which is basically in-depth analysis of each and every topic. Let's say transmission lines, then you're going to talk about the electromagnetic wave or the voltage current behavior in the transmission lines. You're going to talk about impedance mismatches. You are going to talk about the circuit diagram, equivalent circuits. So all of those will be the subtopics, and each and everything will basically be is covered in this particular course. So, uh, so that's why it's essential that you can just look onto the NPTEL videos, basically NPTEL videos, which are basically being uploaded, and the professor has done an excellent job in explaining the things. There is, I should say, no question about it. But what I will be trying to do is that I'll be trying to essentially give something apart from what is being covered. Mostly the professors try to cover the basic concepts. They try to cover the maybe certain problems. They try to show basically certain some complex topics, and they are basically telling you how to derive certain things. So that's fine. That's absolutely fine, and that's just the fundamental of this course or any course rather. But what I will be trying to mainly focus on is application part and where you can see these particular things in real life and what is basically being pursued nowadays. Because I think that is the essential part of any course nowadays. You can just study this course from any of the YouTube channel. You can just study from NPTEL. You can solve the problems, and but but nobody is going to tell you where these particular things are being used. Maybe you can just watch certain videos, but I should say what is basically happening in the research domain or in the industries, or what are people basically interested in solving at, and what are basically they using these, where are they using these concepts for? Is it really having certain applications, or it is just a theoretical manifestation of the mathematical equations? So that is basically what we will be talking about, and essentially, and yeah, most importantly, yeah, we will be solving the problems from the previous assignments. So we'll be solving the assignment problems in the end. These are basically, rather I call them toy problems, because they are very easy problems, and even you guys can solve them. Even if you are just stuck, you can just use certain tools in order to solve those problems. That's not a big deal. Once you have the problem solving skills, you can just easily solve those problems, because they are just formula based, at least whatever is uploaded on the NPTEL portal. So they are easy problems. Mostly they are 10 questions every week. So if we just start solving these 10 questions, it will hardly take 10 to 20 minutes, and that's it. But the essential thing is to build on certain things and to understand why this course is being taught, where this course is being used right in nowadays, I should say in 2026 or 2025. What is basically the update of this course? Where are we heading towards? Is it really relevant? The question is that, is it really relevant to teach the electromagnetic waves course in electromagnetic waves course in 2026, or is it really relevant in 2025, or is it going to be relevant in the future? And if yes, then how? The question is, how is it going to be relevant, and where is it being used? What you can basically understand from this course, and where you can contribute if you are interested in, let's say, you are interested in research, you are interested in job, or you want to work in some maybe industry, you want to work in some maybe defense sector, you want to work in some teaching sector. All of those things basically are essential, and why these courses are important, that these are basically the backbone of all of these things. No matter what you do, either you do research, job, industry, you go to defense, you go to teaching, it's used everywhere. Okay, so the essential thing, oh, okay, I can see a problem here. So here's the professor of this course, Professor Pradeep Kumar from IIT Kanpur. So he's from IIT Kanpur, and I guess he has done his PhD from IIT Madras. And the essential thing is that he has taught so many courses earlier on the NPTEL portal, and he's pretty, I should say, a big name in this particular field, in the circuits, in the microwave electromagnetics. Okay, so what are we going to study today? And these are some of the books and some of the books and references you can basically check. So you can basically go through these references, and one of the other reference which I can add is maybe is something called a Sean series for electromagnetic waves. If you are really interested in solving the questions and in basically understanding the electromagnetics deeply, you can refer to the Sean series electromagnetic waves. There is also one more Sean series vector analysis by Sean series. And this is, I mean, it contains such good problems. It contains very good problems, and these problems are essential to develop that problem solving skills in you. And whether you are preparing for any of the exams, or you are looking for any of the interviews, or you are preparing for, let's say, public service exams, or I should say public service exams, let's say PCEs or whatever they call it, and they are going to be essential. Okay, so now the first thing is that we are going to start with certain things which we are going to recap. This is just a brief, I should say, overview of what is being covered in a week. So even if you just go through this carefully, you are going to understand most of the stuff which is being covered throughout the week. So you have basically, let me just add a page and move this page here. So you basically have Uh, so you basically have week one, and there are five lectures, which is basically L1, 2, 3, 4, and 5. And a professor basically has covered certain things in each of the lectures. And I guess every lecture is 30 minutes each. This is approximate, like approximately 30 minutes each. And what is basically being covered in this particular week one is something called as transmission lines. It's something called as transmission lines. Okay, first of all, the electromagnetic waves, we are talking about electromagnetic waves in, there are two things in guided media, in wireless media. So in guided media is basically, it's something where you can, where the electromagnetic wave basically interacts with certain, I should say, medium. And the wireless is in free space. It's mostly in free space, when the electromagnetic wave just propagates in the free space. So let's say you have the antenna and you are propagating the electromagnetic wave in the free space, and it goes in all possible directions. That is basically wireless media. And the guided media is just like, for example, your circuit. So for example, if you have a chip and you have another chip on a, let's say this is a PCB, printed circuit board, or let's say this is a motherboard of your computer. This is a motherboard of your computer. So the two chips have to communicate with each other. Let's say this is a this is a RAM block, memory block, and this is a processing block. So these are connected by certain wires with each other, and these wires are basically called as traces. This is just a name. You don't need to remember the names every time. So these are just wires, conducting wires, and these are basically guided media. I mean, this is an example of a guided media where basically what is being guided, the certain voltage and currents are being guided. Voltage and currents are being guided. And because it's done on certain, I should say, substrate, certain medium, and certain way is used to basically propagate these electromagnetic waves in certain directions. So this is just a basic example of electromagnetic wave propagation in the guided media. Guided media. Now, you will say that these are voltage and currents and how you are going to treat them as electromagnetic waves. That's basically the question of this particular course. The electromagnetic waves has entire spectrum. So the spectrum, from the high frequency towards the low frequency, you have the cosmic rays, then you have maybe the gamma rays, which are super energetic, so on and so forth. Then you go to the visible region, visible rays, and you have RF, radio frequency waves, you have the microwaves, you have the RF, you have the infrared rays, so on and so forth. I guess the infrared rays comes here, not here. Okay, so this is the spectrum which is mostly from 400 to 700 nanometers, and which you are able to, which is basically visible to the human eye. But what is essentially happening is that it's an entire spectrum of the frequency, which basically it can be which is basically treated as the oscillating electric and magnetic fields. So you have a, let's say for example, this is the amplitude and this is the propagation direction Z, and you have the oscillations in the field. This is basically the electric field oscillation, and then you have the magnetic field oscillations. These are the magnetic field oscillations. And why I have drawn it this way is because if it is a something called as transverse electromagnetic wave, then the electric field and magnetic field components are perpendicular to each other, and they are perpendicular to the direction of propagation. Okay, so this component is basically perpendicular to this component, and they are perpendicular to the direction of propagation. So that's why it's called as transverse electromagnetic wave. So this is just a basic transverse electromagnetic wave, a sinusoidal rather, a transverse electromagnetic wave with oscillating electric and magnetic field components. So this is E field, and this is basically the B field, the magnetic field, and what is basically happening is that you can sometimes write B as mu times H. It's basically you can just write it the magnetic with the magnetic permeability. Sometimes people write it in terms of H, which basically corresponds to the response of the system, and sometimes you can write it B. It's just the notation basically you are following, but you need to take care of the units because there will be magnetic permeability. And what is basically happening now is that once you have, let's say for example, wires, you have two wires or conductors, you have two wires or conductors, and you are just giving in some oscillating voltage, which is basically sinusoidal voltage, which is basically a sine voltage, maybe something which looks like this. It's basically sinusoidal in time. So it's something like sine of omega t. It's pure sinusoidal voltage, which can be, let's say, given with the help of maybe a function generator or a oscillator rather, with that produces a pure sinusoidal wave. What's basically happening is that you are giving in certain time varying uh, voltage to this particular system, and you are exciting this particular system, as a result of which there will be certain current flow, which will be a function of time. And then if you connect a load at this particular end, let's say RL, you're going to see certain voltage across this particular load, which is basically VL. It's just a circuit diagram. But essentially the thing here is, which is important, is basically the length of this particular entire system. So the length is really essential here. If, for example, you are giving any of the, what should I call, sinusoidal signal with certain angular frequency omega, which is basically 2 pi times the frequency, the angular frequency is equivalent to 2 pi times f. So this is exact frequency with which the oscillations are taking place. And if you know f, you can just find basically lambda as c over f. So this lambda is basically this is the wavelength of that electromagnetic wave which is being fed to this particular circuit. Now, what is basically happening is that the essential parameter of this lambda, if it approaches this particular length scale, then there are different phenomena that happen. And it's not only happening in circuit, it happens in a real life also. Even if you have, let's say, for example, you have a spherical object or something, and let's say, for example, it's of maybe radius a or diameter of 2a. Then if you are hitting it with certain light source with certain wavelength, let's say 500 nanometer, and let's say for example this 2a is much greater than 500 nanometer, you're not going to pretty much see any effect. The light is just going to behave simply. It's some of the light is going to reflect, some of the light is maybe it's going to bounce back. There will be shadows of this particular object you will be able to see, and that is just the normal, basically, ray optics you are talking about. Okay, but what happens if you just miniaturize this object to a level of the wavelength of the light? Let's say you make this sphere of the order of 500 nanometers, and you are shining in the light of the order of 500 nanometers. Now, what is basically happening is that, let's say the electromagnetic wave was coming. This is basically a 500 nanometer wavelength, and it's hitting the object of the order of 500 nanometer wavelength. So now basically the interaction is going to happen because this wavelength is exactly of the order of this particular object. So this wavelength is of the order of the object. Now there are certain phenomena that happen basically. This wave can scatter, and you are going to see uh, other different phenomena like scattering. You can also see interference effects. You can also see certain other second order effects because the size is now approaching the uh, size of the waves, basically. Okay, so and this phenomena is similar what happens in basically crystals. If you have a crystal, it's in a solid state devices basically. If you you guys mostly would be either electrical engineers or electronics and communication engineers. So you know about solid state devices, you know about electronic devices, let's say field effect transistors, you know about diodes, you know about silicon, germanium, all of those solid state materials. So you know if you have a, let's say, a crystal, a perfect crystal wherein you have the atoms arranged something like this in a perfect crystalline fashion, and what is basically going to happen is that in these crystals, in these atoms, there are electrons. Each atom has its own electron cloud. So these are electrons for the each atom. And what basically happens is that you know that these electrons are basically particles, but that is classical, but this is classical mechanics. That's what classical mechanics says. But these are basically waves also. That's what basically quantum mechanics told us. Okay. And when these electrons are waves, these electrons are treated as waves. But when are they treated as waves? The question is when, and when are they treated as particles? So because these electrons, they have a wavelength associated with them. You might remember about your class 12 physics about something called as de Broglie wavelength, however you pronounce it. So de Broglie wavelength of an electron is basically something like this, which is Planck's constant divided by mass into velocity of the electron. Okay, you remember this. So if the size of the system, which size I'm talking about, let's say the distance between the two atoms is of the order of, let's say this is the lattice constant A, and this is the distance between the two atoms. And you know this, let's say if you compute the wavelength of electron, it comes out to be of the order of 5 nanometers. Mostly it depends upon the system basically. And now what you are going to basically see is that if now you have a crystal or a system, let's say for example the length of this crystal was L. Now let's say you drop the length of the crystal and it becomes of the order of the wavelength of the electrons. And now these are the atoms, let's say. And now let's say if the length of the crystal becomes of the order of the wavelength of the electrons, what you are going to see is basically the wave nature of the electron and electrons interference effects, the electrons quantum nature, the electrons behaving differently altogether because the length scale has approached the wavelength of the electron. And it naturally happens inside the crystal as well because there are electrons moving here and there inside the crystal. So what is basically happening is that these electron waves are moving inside the crystal, and as a result, they interact with the atoms, they interfere, they produce constructive and destructive interference inside the crystal. The electron waves basically produce constructive and destructive interference inside the crystal, and that gives basically rise to something called as band diagram. If you are aware about a band diagram, or I should say not a band diagram, a band structure rather, something you call as E versus K relationship, which basically looks something like this, E versus K plots. Okay, it's just a general introduction how basically it goes on. So these are different fields where basically the concept is similar. These are basically it's basically everything related to waves, how the waves behave. So it can be either optics, it can be electronics, it can be pure, I should say, microwave devices, microwave physics, or electromagnetics. So this is all related to waves. Okay, and this is a wave phenomena altogether. It doesn't need to be separate in different fields. Whatever you are going to study here or understand here, the same thing is applicable in optics. The same thing is applicable in electronics. You just have to treat it differently. Here you have the electron waves. Here you have the optical waves in the frequency of, let's say, optical frequency. Here you are talking about, let's say, you will talk about microwave frequency, or even you will talk about low frequency, maybe of the order of few hertz, megahertz, kilohertz, depends. And then there is another thing similar, which is similar to it. What other wave is there? There is basically another wave, which is basically acoustic wave. It's basically a sound wave. So that also behaves similarly. If you have a crystal system, you have you have the atoms, and if you just maybe do something to the crystal system by which these atoms start to oscillate, these are always oscillating, but if you externally, let's say, apply even the electric field or if you apply the electric field, these they also perturb basically the atomic systems. We don't talk about those in our fundamental physics courses, but they start to oscillate. And once they start to oscillate, they also form a wave-like thing, which is basically something like acoustic wave. Okay, so they also form sort of a oscillatory motion, and that's why you talk of those acoustic waves as phonons inside the crystal. These are just like the vibrations inside the crystal. Okay, so this is the electronic wave. So these are the phonons, acoustic wave, and similar effects happen with the acoustic waves also. Let's say if the wavelength reaches of the order of certain length scale, you see interference effects, you see scattering, you see all of these second order effects coming into picture whenever the wavelength of these waves uh, become of the order of length scale of the system. Okay, and that is a similar approach which basically is followed in the transmission lines and in the electromagnetic wave approach. So I was trying to just correlate different fields, whether it's microwave or this frequency, low frequency field, whether it's optics, whether it's electronics in the solid states, or whether it's acoustic waves inside the system, crystal system. Okay, so they all are similar because they are waves and they are all treated similarly. I'll just show you certain more examples of how you can relate it in different fields and understand the concept more clearly in all of the interdisciplinary fields, not only the electronics. Okay, because this is really essential so that you can understand how you can just correlate it with different things in your, I should say, in all other courses you have studied. So initially, I'll just quickly go over what basically professor has taught. I'll start annotating using the maybe brown color. That'll be good. So initially, the professor has talked about a transmission line, which basically looks something like this. So you have two cables which are basically connected, and so you have two cables which are basically connected with certain voltage source, and you have a load on the other end. So what is basically happening is that you are feeding in certain sinusoidal voltage here, which is basically a 1 volt signal peak to peak. So peak to peak means from this peak to this peak. That means this is just 0.5 volt, this is 0.5 volt. Okay. And now, for example, you are giving it certain frequency, which is 100 kilohertz, and you are going to compute the wavelength of it, which is speed of light divided by the frequency, and it comes out to be of the order of 300 meters. Okay. So now what's going to happen? If, for example, if you talk about, let's say now this particular system is having certain length, which is of the order of maybe 10 centimeter. Then this 10 centimeter, if length is equivalent to, let me write it, if length is equivalent to 10 centimeter of this particular transmission line, so this is much, I should say, much smaller than the wavelength of this particular, which is basically 300 meters. Okay, so what is basically going to happen? If this is 10 centimeter, if this is 10 centimeter, and the wavelength of the electromagnetic wave, it is around 300 meters. So it's not even going to basically see this particular thing. It will be the wavelength, I should say, of the oscillating electric and magnetic field is not going to impact this particular system, and because this is pretty much smaller than the wavelength of the system. So what is basically now going to happen? If you have a length, instead you have a 10-kilometer wire. So you have a 10-kilometer length, and the electromagnetic wave was 300 meters. That means you have electromagnetic wave something like this, which is basically 300 meters. Now something is going to happen because you have now oscillating and changing electric and magnetic fields through the wires. Earlier, it was in this particular portion, it was around, let's say, constant. It doesn't matter because the wavelength was huge. Now the oscillations are throughout the wire because the wavelength is smaller, the length is huge, Now you are going to see something else. What you are going to basically see is that if you basically have such certain scenario where this particular lambda is much less than the length scale, then what you are going to see is that you are going to see certain delays associated with it. Okay, now that happens because of the nature of the wire you are talking about. Because the length scale of the wire was of the order of 10 kilometers. So whatever you are going to feed it to the wire, the electromagnetic wave, you're going to have certain delays associated. Let's say you feed in input voltage and you are measuring the output voltage. Let's say the input voltage looks something like this. The output voltage can look something like this. That means there is this particular delay associated. I'm drawing it with respect to time. So this delay is basically because of the length scale. Okay, because length is much greater than the wavelength. And now when this delay happens, it is sometimes it's sometimes desired and sometimes not desired. It depends upon the application you're talking about. So when this delay happens, you know that when the delay between the waves happen, this is basically associated with the phase of the wave. And this phase basically is phi, and it becomes a function of length. So this phase is basically a function of length now. That means this length of the length of the transmission line. Okay. So now, based upon this length now, you can play with the electromagnetic waves. You can play with their phases. All right. You can, for example, have a transmission line like this, another one like this, another one like this, and based on this, if you give the input as this sinusoidal waves, you are going to expect certain delays, phase shifts associated at the output. That means if you can engineer the length of these transmission lines, you can play with the phases of basically these electromagnetic waves at the output. Okay, and this is super critical in a lot of applications. I should say critical. Where is it important? You might have understood the theory behind it because professors has talked about it a lot. But where is it basically used and where can you use it? It's basically used one of the, I should say, a basic application now, but it was a big job when this application was when this particular concept was used in certain application. It was a big thing back then, and it's still used. It's something called as there's something called as phased arrays. Phased array is used in radars. It's used in microwave devices. It's used in something called as anti-drone jammers. It's used in satellites. It's used in imaging, basically the satellite imaging. It's used in, I should say, drones. It's used in every system you are encountering in today's world. And how is that being basically used is that you have certain devices. Let's say you have certain devices, microwave devices, which are transmitting the microwaves. So this is one microwave device, this is second microwave device, third, fourth, so on and so forth. Okay, and these are emitting microwaves. Let's say, for example, this is a radar antenna. Okay, and it's emitting microwaves. Let's say, for example, the object is somewhere here, but the antenna, which is basically this antenna, it's facing this direction. So the electromagnetic waves are mostly going in this direction. Some of them are also going in this direction, but mostly the direction is something like this. Okay. Now what is basically happening? You want the you want to tune the directions of the electromagnetic waves in such a way that they are mostly in this particular direction, so that when you get the reflection back, they will be detected with higher efficiency. How you do it? You can do it basically by simply turning the entire antenna, right? This entire thing can be turned like this, turned like this, and it's going to emit the microwaves in this particular direction where it is going to hit the objects and you are going to get the reflections back. This is one way. This is the old way. You are not every time going to turn the radar, or you are not every time going to basically move the big thing altogether. Or in certain applications, you are not going to move the antenna itself. Okay. What you want is that you want this antenna to be stationary, but you want the electromagnetic waves to go in the other direction. That means you want the antenna to be like this, but the electromagnetic waves should go like this. Okay, so that it can hit the object here. How are you going to do it? That is basically the trick behind phased arrays and where these phases are used. So what you do is that you basically what you do is you give certain because this basically is a transmission line. So you feed in certain voltage and it gets delayed a little bit. At one, it is having certain delay. At second, at third, at fourth, it's having different delays. And you know those delays are basically phase delays in the waves. Okay, let's say for example, this is having a delay of zero point 0.1 pi, this has zero point 0.2 pi, zero point 0.3 pi, zero point 0.4 pi. Okay, radians, in radians I'm talking about. So what is the delay? It is a sine of omega t plus some phi. Okay, so this is basically a phase particular. So you can delay it. If you have something like sine, you can basically draw something like this, and you can also draw something like this. So these are all delayed versions of the sine. Just like you have sine of omega t, something you can write sine of maybe pi by 2 minus let's write it omega t minus pi by 2. You can write it in terms of the cos. Okay. So because the cos is just the delayed version of the sine. That's it. But now the essential thing is when you give certain voltage here or wave, it gets delayed at each of the, I should say, microwave device. This is basically a microwave device which is emitting a microwaves. So once the wave gets delayed, what happens basically because of the delay? So let's say, for example, this wave is something like this, and this wave emitted by this is maybe something like this. The another wave is something like maybe this. I'm just drawing it not exactly because this is just looks like a phase flip of pi. I'm not drawing it to the scale. I'm just trying to make you understand the concept. And this way will look something like this. What happens? Basically, what happens now is that these all waves now start to interfere with each other because they have a difference in phases. When they interfere in such a way they create constructive and destructive interference patterns. That means if this was an antenna array, it creates it is emitting the wave something like this. These are the wave fronts emitted by each. So they are moving, they are moving, they are moving. It creates the interference in such a way that most of the constructive interference happens and it goes like this. And there is basically what happens is, let me just draw it this way. When the interference happens, the constructive interference happens in this particular region mostly, and all of the destructive interference happens here. This is destructive interference. And the beauty is that because of constructive interference, these waves altogether go in certain directions and hit the object here, and they are reflected back, and you can get them. Now, what you have done is that you have basically steered the beam. You have changed the direction of the beam from this direction to this direction without moving the antenna. And this beauty is because you have the phases associated with the waves, and you have used those phases to direct the beam coming from the antenna. Okay, and that's basically what happens in phased arrays. So you do something called as beam steering. You steer the beam in certain directions because of the constructive and destructive interference. This is just a one example I'm talking about how important this is basically in today's application, today's world. The same thing is basically happened in satellite imaging. It's used in drones. It's used in I should say jammers. It's used in microwave devices, so on and so forth. So this is just the one example. Okay, now what is basically happening is in this transmission line, because now you are talking about the length scale. So this length scale, when it becomes of the order of wavelength, you know that professor has talked about it, that you have to use the transmission line approach. Okay, and now where these transmission lines can come into picture, they can be guided transmission lines, just like a trace. If the two circuits, if the two boards in a circuit are being connected by certain wire, it can be treated as a transmission line. If there is a, let's say, substrate, then there's a dielectric, there is substrate, and there is a metallic strip over it. You can basically guide the electromagnetic waves through this metallic strip, and this acts like a transmission line. You can basically shield this metallic strip, and it can also act as a transmission line. Why this shielding is used? Because the electric field and the magnetic fields uh, they also leak from the substrate. So if this is, for example, the I should say the strip which is carrying the electric and magnetic field, so this is carrying the electromagnetic wave. So there are electric and magnetic fields basically which are being propagated in this direction. So this is just like fields I'm drawing, not to the scale, but they are basically coming out from this particular system. So they are also the fields in space, free space. So that's why, because these fields are always there in the free space, whenever the electromagnetic wave moves, even if you have a wire carrying the current at certain frequency, because of the current, the magnetic field is associated with it. You know, there is a magnetic field associated with it. And then you also know that this particular scenario, uh, this particular current creates the magnetic fields, and this also behaves like an electromagnetic wave moving, propagating throughout this particular system. So whenever you have this electromagnetic wave propagating, it's not only the electromagnetic wave that is basically localized in this particular wire. The fields are basically coming out from the wire, and they are also in free space. Okay, and that also happens at the chip level. Although this, I should say, the electric field and the magnetic field coming out from that particular system, this is very small length scale associated, but it's always there. So that's why most of the time the shielding or shielded microstrip is used, so that the electric and magnetic fields stay shielded, even from the external interference. External interference means if now, for example, there is a microwave uh, in the free space coming from certain other source. Okay, they can basically interact with these particular fields. And if that interaction happens, it can mess up with your system. It can mess up with your mobile phone. It can mess up with your circuits. So basically, you won't be able to use your phones efficiently. Okay, so these microstrip, or I should say the transmission lines, these are everywhere. Let's say, for example, let's say these transmission lines are, I'll give you a very good example. Let's say these transmission lines, let's say this is your mobile phone, and it's having certain processor or chip, whatever you call it, and these chips are having certain components. There are wires which are basically metallic, gold, or whatever the material is used to basically carry the currents and the voltage. So at that particular level, because because you are processing the information at a very high frequency, sometimes you might be knowing about what the processing speed. It can go up to 5 gigahertz, maybe it can go up to 2 gigahertz. So what is this basically gigahertz? These are basically the uh, at this particular frequency, these particular oscillations are taking place. Okay, Now, every time they are carrying currents, there's a field associated with those currents in that particular system. So that's why every time you are using even any of the electronic devices, whether it's your laptop, whether it's your mobile phone, whether it's your any of the electronic gadget, there's always these fields associated with that particular system. And those fields are very small. They don't usually come out of I should say, come out in a huge region of a free space from your electronic device, but they are localized to the electronic device. That's why there is something called as SAR rating, which is basically the radiation rating and something else associated with an electronic device. And if some, for example, external wave comes, which is basically a high frequency wave or super energetic wave, they can basically interfere with these electric and magnetic fields. But that's why most of the time they are shielded. So the shielding is done in order to protect these devices from the interference effects. But sometimes the shielding can also fail if the wave is super energetic. Let's say uh, maybe let's say for example, what happens is that if this is Earth and there is some cosmic event or cosmic rays basically being emitted from certain collision of the stars or something else, and you're using your mobile phone on the Earth, what basically happens is that these cosmic rays can also these also can hit the Earth, and they can penetrate certain layers of our atmosphere. They can interact with the electrons in your electronics. Okay, and they can interact with these fields, and sometimes the electronic gadgets stop working, and more it's basically related to the events basically happening in the universe. And that's one of the things why these electric and magnetic fields are basically important, and why it's important to shield those particular devices. That's why in satellites altogether, most of the electronics are basically completely shielded. They try to shield it at least as much as possible, because the space is completely, I should say, filled with these particular cosmic events. Okay. Now, what is important here is that I'm not going to talk about the details which Professor has told already. I will just go into how, where is this? Yeah, so uh, we were talking about the length scales. So when the length scale approaches the wavelength of this particular electromagnetic wave, you have the transmission line theory, which can explain how the transmission of those waves takes place. And if you have the length scale which is much greater than the lambda, you have the ray optics. That means your normal rules of reflection, refraction, your even diffractions, they all are applicable in this particular length scale. That is basically the normal uh, day-to-day life which we are talking about, because length scale is mostly much greater than the wavelength scale. So that means if there's a human being standing here and there's another human being standing here, so this human being is able to see this human being because there is electromagnetic waves, visible rays coming from the sun or from some light source. They are hitting this human being and they are getting reflected to the other person's eye. So that's why he's able to observe this particular being, because the length scale of this human being is much greater than lambda. Now, what happens if you have a bigger human being, and if you have another being, I don't know if it's a human being or some micro being, let's call it micro being. If let's say the wavelength of light, visible light is coming, which is of the order of 500 nanometers, and if this being is of the order of 500 nanometers, will you be able to visualize, will you be able to see this particular being? And the question is, if yes, question is why, and if no, the question is why not, and what is basically going to happen, and what is further going to happen if this human being shrinks down to the size of, let's say, 10 nanometers, which is even far less than the wavelength of the light. So you pretty much cannot see it, because this is this particular visible light is not going to interact with this 10 nanometer. Okay, that's why uh, you need to use certain wavelengths which are of this order, 10 nanometer. Okay, that's why whenever you do microscopy, you see that you cannot see below certain length scales, because if the length scale goes less than the wavelength you are using, you pretty much cannot use it. You can, because it does not, it will not interact in the similar fashion. That's why if you want to see a very small scale, you use wavelengths which are of the order of that small scale. Okay, most of the times then you have to go to, let's say, X-rays, but you cannot use gamma rays. They are super dangerous. If you want to see it, maybe it can destroy it, but you want to go to X-rays because the wavelength is of the order of maybe 10 nanometer or 5 nanometer. Okay, that's why there is something called as X-ray diffraction technique, which people call as XRD, I guess, X-ray diffraction. And this is used to visualize the crystals because the crystals and the atoms, they fall in the, I should say, similar regime, okay, of the order of these few nanometers. So that's why X-rays are used there. You cannot view crystals in with a visible light. There is no way because visible light is 500 nanometers. Okay, so the system and the size of the system is essential. That's what I'm basically emphasizing here. It's always essential. What is the size of the system compared to the wavelength you are using to interact with that system? Okay, so now you have another thing. Let's say, for example, you have a transmission line. You want to see how to model this particular transmission line. That you are feeding in some voltage, which is the source voltage, and you are having certain source resistance, which is always there because there are always losses. Okay, and it is propagating in this particular direction, and it's being fed to the load. Now you want to understand what is basically the voltage level at this particular point and at this particular point because there is certain length associated with this, which is L. And now because there is length associated, you I talked in the previous slide that there will be a phase associated, which will be a function of length. When there is a phase associated, so there will be delays in the wave propagation. So this is all related to waves. So if you are familiar with how waves move, how waves propagate, you're pretty much good to go with this course. And now we need to relate the voltage and the currents to the electric fields and the magnetic fields, and also to the locations. What is the voltage at this point? What's the voltage and current at this point? So let's say this will be volt current at particular Z. This will be current at particular Z plus delta Z, which will be some small distance. So we need to basically compute those. And and you know from your basic physics that how you can relate the voltage and currents to electric fields and magnetic fields. You have to use the Maxwell's equations, which are basically you can use Maxwell's all of the four equations in order to understand how basically spatial variation of space, time, variation of fields basically occur. Electric field and magnetic field occur. Okay. And now, for example, you have, let's say, for example, the phase I was talking about. Let if you have a transmission line, there's a phase associated with the waves, which is a function of length scale, this length. And this particular phase is basically given by 2 pi length over lambda. So this is basically the phase associated. Where does this come from, by the way? This is basically the delay. And this is basically something called as, it's mostly called as, you can also call as wave vector in other physics domain. This is written as k equals to 2 pi over lambda. So you can write phase as k times L. I don't know whether it's written as beta here also. You can write it beta or k, but this is something called as propagation constant or the wave vector. So this is, and you see that this is a dimensionless quantity. This is a dimensionless quantity. Why? Because it's inside the sine. So you have sine of omega t plus phi as a function of L. So this has to be dimensionless. And it is dimensionless because it's 2 pi over lambda times into L. So the unit of this is meter. So this is meter. This will cancel. This dimensionless. Okay. Uh, so now what is basically happening is that now you need to understand basically if you have a wire of length L, when these electromagnetic waves flow, how are you going to model this particular wire to understand the voltage and the currents? And when you model, you have to model it from the circuit perspective. Okay, because you have to make understand it in terms of resistances, capacitances, inductances, because that's what we basically know. And what happens is now naturally whenever a wire is carrying a current of I, it has a magnetic field associated with it, and this magnetic field basically can be modeled as inductance. Okay, and naturally this wire has certain basically losses associated with it, and this is because of the material. This loss can be, by the way, I should say, this loss can tend to zero if you design it in a certain way. Let's say, for example, you have superconductors, then this R can tend to zero, but the inductance and the capacitance is always going to be there because these are uh, just the I should say certain, but these are, I should say, the parameters which are always going to remain there, no matter what, even if you can make the resistances go to zero, because these are associated with the motion of the electrons, motion of the currents inside the wire. And the current is always going to flow in the wire. It will flow lossless, it will flow without any losses, but it's going to flow. And whenever the current will flow, it will give rise to magnetic field, it will give rise to electric field, and those two things are basically associated with inductances and capacitances. Okay, so that's the fundamental point. That means, for example, if you have a wire, the transmission wire where the current is basically going, you have V positive, V negative in these two transmission lines. These are the voltages because of the charges now, because there will be charges flowing in this particular wire. Let's say this will be positively charged, this will be negatively charged, and there is a free space in between. This is going to act like a capacitor. It's going to act like a capacitor where there is certain dielectric in between. There's a positive charge, there's a negative charge. It's just a basic example. And sometimes this is not even free space. This is certain dielectric. It's even a substrate or something. Then basically what's going to happen? It's going to have uh, certain charge storage. And whenever there is charge storage, this is basically associated with capacitance. Okay, just like in a diode, you know that if this is a P, this is N, you have positive immobile ions in the diode in this region, which is basically called as space charge region. Space charge region. Then you know that this particular thing acts like a dielectric, and if there are charges present here, electrons on the N side, holes on the P side, this can give rise to a capacitance. So it acts like a capacitor, where these are holes, these are electrons, so these are positively charged, these are negatively charged, and in between you have a dielectric, which are immobile ions. So these are immobile ions, and they basically give rise to a capacitance. So that's why you have the concept of junction capacitance, depletion capacitance in the diode. Okay, so the capacitance arises everywhere where there is charge storage, and the inductance arises where there is a time varying current flowing through the circuit, through any of the wire. It doesn't have to be circuit. So that's why there is inductance associated, there is resistance associated. Now, why are these measured per meter? Because you're talking of the length scale. Okay, every time you're here talking about the length scale, you have to talk of the inductances and the capacitances in terms of per meter. How much is the inductance per meter and the capacitance per meter? So that's why you're measuring it Henry per meter and you're measuring it ohm per meter. Okay, because you're going to see in the equations whenever we are going to write KVL or KCL, let's say for example resistance, inductance, capacitance, whenever we are going to write KVL and KCL, we are going to write it as R times delta Z, L times delta Z, C times delta Z type, or I should say yeah, C times delta Z, so as to make sure that ohm per meter and meter goes off, and the only ohm remains. Similarly, Henry per meter times meter, or capacitance farad per meter times meter. Every time we are going to do this, just make sure that the actual unit is going to remain, but we are going to measure it in terms of length scale, because that's what basically we are measuring here. We are going to measure its effect with respect to the length scale. Okay. Now, what is basically happening? Now, these are called as distributed parameters. What these resistances, inductances, and capacitances that arise in a wire or in a conductor because of the this arise because of the losses, because of the material, this arise because of the magnetic field, because of the flow of the current, and this arise because of the charge storage. Okay, so they are distributed. Why? Because they are not localized in a single part of the wire. So for example, if this is a wire, so you cannot say that the resistance, inductance, capacitance, and inductance is only in this region. No, it's basically in the entire region. These are basically modeled as lot of inductors and capacitors in uh, consecutive fashion. Okay, so this is entirely distributed throughout the region. And now if you have inductances and capacitances throughout the region, most of the time it's basically something like this. You have the inductance, resistance, inductance, and you have the capacitance, something like this. So you have the resistance, inductance, capacitance, okay, and you have inductance, so on and so forth. So this is basically how it's viewed. This is basically the circuit model of a transmission line. Circuit model of a transmission line. And why is the capacitor present here and not here? The reason is because there's a charge storage of opposite charges in these two transmission lines. Because this is positive, this is negative. So this plate will be positively charged, this plate will be negatively charged, and there will be some sort of a charge storage. Even if it's temporary or if it's transient, it's going to act like a capacitor. Okay, that's why the capacitor acts between the two transmission lines and not here. Okay, and the resistances and inductances are always. That's why that's why you don't have inductance here, because because there is no current flow in this direction. Okay, current is only flowing here or here. There is no current flow here. There can be something called as leakage currents, but that is not of our concern. We'll talk about it later, because a capacitor, okay, the leakage current can flow through a capacitor, but that's basically a short which is not desired. But that's why the inductor doesn't appear here in this direction. Okay, but there is also a resistance associated with the whatever the space is filled. There is always the resistance associated. So that resistance is present there, but there is no inductance because there is no current flow as such, and there will be no time varying current. There will be no magnetic field associated with it. At least ideally, but practically there is always, I mean, some part. It's very small. Okay. Now, when you have a distributed system, something like this, what are you going to do is that you're going to model it. And how are you going to model it? You're going to model it by considering small section of it, or let's say of the order of delta z. When you consider the small section and you zoom in it, you have a resistance, you have inductance, you have a capacitance, and you have a resistance again. So this is basically how the transmission line looks like. And now you have to apply the KVL and KCL in this particular system in order to evaluate these parameters, V as a function of Z comma T, the currents, and the voltage on the load side, the currents on the load side. So this is basically the input side, this is basically the load side. And now you have to solve the KVL and KCL. That's what I'm not going to do here, but we're going to see what basically we arrive at. So when you write the KVL, how you write a KVL? If you have resistance, inductance, capacitance, resistance, and you have V as a function of Z comma T, and you have I Z comma T flowing here. This is R, L, This is basically R delta, rather I should say, yeah, that's what I was talking about. R delta Z, L delta Z, C delta Z, G delta Z. Why do we write it as G? It's because G is 1 by R. So that's the reason. And this is the output. So you write the KVL by going in a loop from this point to this point. Okay, so you go in a loop like this. So you have minus voltage plus the current times the resistance, which is basically voltage again, plus the inductance times the variation of current. This is basically L di by dt. For the inductance is basically this is the voltage across the inductor. And then you write the KVL again from the output node, which is basically this node, not exactly like this. So you solve these particular equations, you arrive at this particular relation, which is basically the variation of the voltage with respect to the uh, z direction, which is basically the spatial direction. Again, you write a KCL. Basically, the KCL is used at this point. So there is incoming currents and then there is outgoing currents. So you have all currents going in plus, I should say, all incoming currents plus all outgoing currents should add up to zero. Okay. And when you apply the KCL, you have you have the IZ comma T here. You have IZ plus delta Z comma T coming in this direction, and it's going to the capacitor and the resistor. This is the capacitive part. Basically, the current through a capacitor is C dV by dt. So this is the capacitive current. This is the current through the resistor, which is basically G times voltage. That means the current is basically V by R. This is basically 1 by G is equal to 1 by R. So, okay, so I hope this is clear. And when you solve this particular equation, you arrive again at certain set of equations with respect to a space, which is basically dou over dou Z. That's what we basically want. We basically want to see the variation of the voltage and the current with respect to a space. We also want to see it with respect to the time. So that's our main goal. So now what we do is that we approximate it and we let the delta z tend to 0. What does it mean? It means that this particular region becomes entirely small now, this particular region. Okay. If it becomes very small, then what is basically going to happen? The wherever you find the delta z, that's going to vanish. And now you are going to consider something called as r equals to 0 and g equals to 0. It's basically something called a lossless line. Okay. And then wherever you have a lossless line, what is going to happen? You have very negligible losses in the system, in the transmission line. And when you have negligible losses, you arrive at particular relation which looks something like this. Something like this. That means the variation of the voltage, the second derivative of the variation of the voltage in space is basically LC times d square V by dt square. This LC is basically 1 over mu square P. Okay. And this is basically square here. And it almost looks like a, if you are familiar with the wave mechanics, or if you are interested at it, it looks like a wave equation where this is d square v over dz square is equivalent to some velocity times d square v over dt square. So this is basically a wave equation. So that means these voltage and the currents are basically moving as waves in the transmission line. Okay, and uh, if you have, let's say, for example, this LC, it can, maybe you have denoted it as UP square. So this can act like a, I should say, the how fast the waves are moving in this particular transmission line. That's why there's a velocity term here. Okay, so it basically denotes how fast these waves are basically moving. So how fast the wave will move through the transmission line will depend upon L and C. Why? Because these are the elements which cause delay in the line, delay in the electromagnetic waves through the transmission line. Why? Because let's say if you have a transmission line and the electromagnetic wave was moving like this, and Because of the capacitance, there is charge storage, at least temporarily. Because of the charge storage, if the charge gets stored, it is going to impede the motion of the other charges, other electrons, because at the end there are electrons flowing. Okay, so what's going to happen now? That's going to cause a delay, and that's going to slow down the motion of this electromagnetic wave. That's why these inductances and capacitances basically uh, slow down, or they are basically the governing factors of the I should say the speed of the wave inside this medium, inside the transmission line. I should say speed of the wave in transmission line. Okay, so uh, now what is basically happening is that if you have, let's talk of this scenario. Now, if you have a transmission line, so you have a source current going in this direction, then there will be some current returning in this direction. And in the source current part, there will be basically some positive current, there will be negative current. This is basically the incoming part and the outgoing part, incoming part and the outgoing part. So these are basically the phenomena associated with the waves. So how I will make you understand is, if you, let's say for example have a, let's say for example you have a barrier here. This is a barrier, and you have some wave coming here. Some part of the wave is going to get reflected, some part of it is going to get scattered, maybe some part of it's going to get, let's say, transmitted through the barrier. This transmission part is basically dependent on the length of the barrier. If it is a, let's say, the electrons wave, then this transmission part basically is called as tunneling there. But this is just a wave, and this is just a barrier I'm talking about. But all of these phenomena happen in real life. Let's say for example, let's say for example, you have a surface of water, and you have some, let's say, source which is emitting sound, basically an acoustic wave. So you have acoustic waves coming in, they are hitting this water surface. But what is basically happening is, here the acoustic waves were moving in air, but here you have a water. So at this particular region, there is basically impedance mismatch. What is impedance mismatch? It basically means that the medium has changed altogether for the waves. The waves were moving in air, but now they have to enter water. They cannot just go inside because the properties are different. What properties? Because acoustic wave is a mechanical wave, a sound wave, so it depends upon the density and the speed of sound, you know. So for example, if the density of the medium of the air is rho 1 c1, this is density is rho 1, speed of sound is c1, and the density inside water is rho 2 and c2, you know what's going to happen? There will be, at this point, there will be impedance, hindrance to the wave motion, impedance to the wave. And you write it in terms of z equals to basically this product rho 2 c2 minus rho 1 c1 divided by rho 2, I should say rho 2 c2 plus rho 1 c1. Where does this come from? Just forget about it. I'm just talking about the concept. And by the way, this is not even impedance, this is basically reflection coefficient. This product is basically impedance. This is impedance. Okay. So what I mean to say is that if this is water, there is acoustic wave coming in. You have rho 1 C1, which is basically the impedance of the air. This is impedance of air to acoustic wave. Then you have Z2, which is basically rho 2 C2. This is impedance of water uh, for the acoustic wave. And because these impedance values are different, this is different, this is some value, this is some value, they are completely different because the density of water is much, I should say, larger than that of the air. Okay, because it's dense. Speed of sound is also different. The speed of sound in, let's say, air is 340 meter per second. In water, it can vary. It is temperature dependent, but it can go around 1500 meter per second. So because of this difference, when the waves come in, they have to they have to somehow manage because the mediums are different. As a result of which, some of the waves get reflected. not some. In this case, most of the waves get reflected. Most of them reflect. And that reflection is basically denoted by something called as reflection coefficient, R, which is basically Z1 minus Z2 divided by, rather it is Z1 minus Z2 divided by Z1 plus Z2. Okay, so this is the reflection coefficient. That is the similar thing what happens basically here in case of electromagnetic waves. If you have certain waves going in this direction and it encounters certain load, which is basically RL, if the load is not matching with the characteristic impedance of the transmission line, let's say this is Z0 and let's say this is ZL. If the Z0 is not matching ZL, there will be reflections of the wave. Of what wave? Electromagnetic wave. Similar to this particular phenomena. These are waves at the end of the day. Okay. So these get reflected, and you talk of reflection coefficient here. You talk of similar reflection coefficient which is basically given as, I guess, Z1 minus Z2 divided by Z2 plus Z divided by Z1 plus Z2. But these Z1 and Z2 quantities are related to voltage and currents. It's not related to density and speed of sound. It's different because we're talking of electromagnetic waves. But the phenomena is similar. Okay. And now I won't go to the equations because it's pretty much straightforward to understand the equations. Even the professor has talked about it. What I will talk mainly is now where does this impedance come from and how you can compute that impedance. Where is the impedance part? Uh, uh, mm, yeah, this is the forward and backward part. This is the characteristic impedance I'm talking about. Okay, so this is the characteristic impedance of the transmission line. That means the transmission line has its own impedance, which depends upon resistance, capacitance, inductance. It also depends on frequency because there is omega. But what happens if the transmission line is lossless? That means if the transmission line is lossless, then R and G are zero, and you get Z naught to be equivalent to under root of L over C. That means this impedance is dependent on the L and C. Impedance of what? Impedance of electromagnetic wave via transmission line. That means these inductances and capacitances are going to denote how slow down or how fast the electromagnetic wave is going to move through the transmission line. That is basically the essence of it. Okay, and uh, now whatever you want to connect at the, let's say for example, load end, you would want to ensure that this ZL is at least matched to Z0. Why? Because if this is matched, if these two are matched, then the reflection coefficient, which is ZL minus Z0 divided by ZL plus Z0, this will be zero. That means there will be no reflection of the wave. That means when there is no reflection of the wave, anything that you apply at the input, let's say you apply 10 volt, that is going to appear across the load, and you will see 10 volts here if there is no reflection. But if there is reflection, most of the time, which is the case, that ZL is not equivalent to Z0, then there will be some reflection. Let's say some reflection of let's say 0.5. That means half of the electromagnetic wave is going to get transmitted. I should say reflected, and you will see only half of the voltage maybe here. Let's say 5 volt. The number is not exact. I'm just making it trying to make you understand it. So that is basically the concept of the reflection coefficient appearing here. Okay, and if you talk about the something called as maximum power transfer, this is also a theorem, but this is just a name. It doesn't matter. The names don't matter. It should be the concepts matter basically. And maximum power will be transferred when the impedances match. Impedances match, and that is basically this that the characteristic impedance and the load impedance are exactly similar. That is basically the concept. And if now you have basically, but at the end of the day, this characteristic impedance is basically a frequency dependent thing, frequency dependent. That's why if you change the frequency, you are going to see the change in the characteristic impedance of the wire. Okay, that's why if you, for example, have a wire, if you have if you feed it with a sine wave of, let's say, 5 kilohertz, you are going to exactly see 5 kilohertz here. I'm not talking about talking of amplitude, I'm talking of frequency only. But what if you feed the 5 gigahertz? Are you going to see 5 gigahertz here? The answer is no, because the characteristic impedance depends on the frequency. You're going to see if the 5 gigahertz, if the 5 kilohertz looks like this, you will see something like this. But 5 gigahertz will look something like this. And you're going to see a lot of distortions here. Why? Because there will be huge impedance in this transmission line to this 5 gigahertz electromagnetic wave. And now how are you going to transmit the 5 gigahertz then? You need to use a different transmission line. You need to use some different approach so that you can make the 5 gigahertz electromagnetic wave transmit through these particular lines so that your impedances are basically reduced. That is basically the engineering part. And that is basically the essential part of microwave engineering. Okay, that how you want to transmit these high frequency waves, which are, let's say, 5 gigahertz, which are maybe 10 gigahertz, 100 gigahertz. So this is basically for radar. This is for Wi-Fi signals or your mobile phone signals. They are at 5 gigahertz. They are at 2.5 gigahertz. They are basically being processed inside your system. It's basically the thing is that at the phone level they are not exactly 5 gigahertz because they are down converted. But at the end of the day, you want to transmit certain high frequency. So that's where the microwave engineering part comes into picture. You design these transmission lines in such a way so that they are able to transmit these high frequency signals. That's the part of this characteristic impedance. And now, what else is there? This is the reflection I was talking about, the reflection coefficient R. And where is the relation for it? You see the reflection coefficient, it depends upon the ZL minus Z0 divided by ZL plus Z0, which is basically the load impedance, and this is the characteristic impedance. And if the load impedance is equivalent to the characteristic impedance, you see that gamma L drops to 0. That means the reflection coefficient goes to 0 and you have maximum power transfer. That means to the load you get the maximum power. That's it. That's about it. Now, what else is being covered in this session? These are basically the mathematical equations you can go through and have a look at. These are don't involve, I should say, much explanation. And what else was there? I think the voltage standing wave ratio. I think let me see if we can cover this. Okay, let's cover it in the questions itself. Let's move to the question part and see if we can just cover what things can be covered here. Let's say we have the first question, which is basically the characteristic impedance of a transmitter. No, the first question is which of the following statements is correct? So the first part says that the length becomes of the order of wavelength. That means if this is the transmission line, if the length is of the order of wavelength, you go to a transmission line approach, which that is what I was talking about in the slides, that you treat it basically in terms of waves because the length has approached the wavelength of the electromagnetic waves. So you treat the currents and the voltage as if they are the waves, electromagnetic waves propagating inside the, I should say, transmission line. So L is much, much less than lambda is basically lumped circuit regime wherein you are treating the, if you have, for example, length, and this is much, much less than lambda. That means, let's say lambda is of the order of, let's say this is, uh, what should I say, 100 meters. And if this length is, let's say, mm, how should I say it? Let's say this length is one centimeter. So essentially, what is going to happen is that the wavelength through this entire region is going to remain uniform. It's not going to change. A wavelength, the wave is not going to look at it. I should say uh, differently. It's going to stay safe in this particular small region. So it can be treated as a certain lumped element. Okay, a single element of a, let's say, a resistance, capacitance, and an inductance. Most of the time, resistance, inductance, and a capacitance. But what happens if you have a length scale which is much, much greater than lambda? Then it's the normal ray optics, which is basically light coming in, getting reflected, sudden transmitted, because this object is much, much greater than the wavelength of the light. That's basically the answer of this question. So the answer will be all of the above for this particular question. And now the second question, the characteristic impedance of the transmission line is defined. So we define the characteristic impedance right now, but it is also defined in terms of the currents and the voltage. How? If you have a transmission line of length L, you know its characteristic impedance is basically Z naught equals to under root of R plus J omega L divided by G plus J omega C. But this is in terms of the inductances and capacitances. You can basically solve the previous equations which I showed in the slides, and you can show that if you have, for example, a positive traveling wave in this direction, let's denote that as V plus, and this is V minus. Then you have the source current flowing in this direction. This is the returning current in this direction. Basically, you can compute the ratio of positively going currents to the, basically, the current the current going in this particular I should say line, and that is going to give you the characteristic impedance at that particular point. So this will be the characteristic impedance. That means the ratio of positively traveling voltage wave to the current wave at any particular point is going to give you the characteristic impedance. Okay, because because the because the current waves flowing like this, they will also have certain parts which are going in this direction. Similarly, in the bottom one, there will be certain current directions associated with it. So that's why this particular ratio gives you the characteristic impedance. It cannot be the first one because you have positively traveling voltage wave, negatively traveling voltage wave. If you take the ratio of it, it's never going to be impedance because it's going to be unitless. But the impedance has certain units, and that is only possible if these quantities are different in the numerator and denominator. So this is the option. And the second option is not possible. The characteristic impedance is not the input impedance. Input impedance is something which is basically seen by the source from the input side. So if this is in source, whatever is seen by the source from this side, basically this region, it's basically computed as input impedance. It's basically whenever the electromagnetic waves start to propagate, when they initially hit this particular or enter this particular system or transmission line, that is basically considered as the input impedance. Okay, whatever is seen by the seen by the source from the input side. From the output side, there is basically something called as output impedance. Okay, now for example, if this is a source, and if you connect this source to a, let's say, a MOSFET, which is a field effect transistor. Let's say you have a source, you connect a source to the MOSFET. You have a gate terminal, and you have a drain terminal. You have source terminals. So this is source. So this is gate terminal, and you just ground it. So what will be the input impedance? That will be this particular impedance, this particular part. what will be the impedance seen by the electromagnetic wave on this particular side, because you are applying, let's say, the input wave to the gate, and you know this particular impedance because there's a dielectric present between the gate and the substrate. So this dielectric, it won't allow the electromagnetic wave to propagate. That's why this input impedance, the source from the source side, it becomes infinite. So that's why you see that the input impedance of a MOSFET is basically infinite. Why? Because it's completely impeded. You cannot The electromagnetic wave cannot go through because there's a dielectric. Because this is the MOSFET. This is source, drain, dielectric, gate. This is gate terminal, which is a metal. So nothing can go through this, at least ideally. So the impedance is infinite. So that's why input impedance is infinite. So that's the impedance basically seen from the source end. And the output impedance is basically something, if this is the output connected, which is V output, so this is basically the output impedance seen from the output side. That's a different thing. Okay. That the transmission line is said to be lossless if, when is the transmission line said to be lossless? It's the simplest one, when the resistance falls to zero. That means the resistances you are considering uh, here and here, if these resistances go to zero, then it is basically a lossless transmission line. And in a lossless transmission line, there will be actually only inductances and capacitances. There will be delays associated still. A lossless doesn't mean that there will not be delay, because the delay is controlled by the capacitances and the inductances. Okay. Lossless just means that amplitude will not be affected, but there will be always phase delays. That means if you have two transmission lines, one is like this, and you give in a sine wave of peak to peak 5 volt, and what is going to be at the output? It's going to be, let's say, certain delayed version of it. But it's going to be let's say 2 volt. But there will be, the amplitude will reduce, and there will also be delay, which is basically a phase delay. But what happens if you remove the resistors? If you have only inductance, and if you have only capacitance, whatever you're going to give at this end, let's say this is 5 volt, it's going to appear at the other end, but with some delays. This will also be 5 volt, because these do not consume anything. These are just elements which are going to cause the delay. But the amplitude is going to at least ideally stay same. I'm talking of ideal situation, not practical, because practically there is loss associated with inductance and capacitances. But ideally it's going to be similar. So this is the scenario. A lossless transmission line with inductance is given, characteristic impedance is given, frequency is given. You have to compute the phase constant, which is basically beta. So the beta, how it is basically related. So you have a lossless line, that means R is equal to 0, G equals to 0. That means you can write characteristic impedance as under root L over C, right? And you have the phase constant, which is basically given as omega under root of LC, is basically the phase constant. Then what is basically you need to find? You need to find the phase constant associated. Frequency is also given. Inductance is given. The characteristic impedance is given. From this you can obtain the capacitance. You can obtain the C from here. Once you get C, you are going to use the C in this particular, and you get beta, which will come out to be approximately equivalent to 673.2 radians per meter. That's as simple as that. So this is the answer of this particular question. Moving on, the lossless transmission line with L equals to 1 micron characteristic impedance, its phase velocity. This time the phase velocity is to be computed. And the phase velocity is basically given as, let's say, phase velocity is some frequency divided by the previous quantity which we obtained, phase constant. Okay, and what we need to obtain? I think we have obtained beta, which is basically uh, obtained in the previous question. Beta is 673.2 radians per meter. You can obtain the phase velocity as 2 pi 5 gigahertz divided by 673.2 radians per meter. And once you obtain this number, you're going to obtain the phase velocity of 4.6 in 10 to the power 7 meter per second. Okay, and I'm not going to go into discussion of what is basically a phase velocity and group velocity. These are two different velocities associated with the waves, and most of the time information travels at the speed of group velocity. And this phase velocity, it can also exceed the speed of light, by the way, light speed. It can be greater than speed of light because it's not actually the information. It's not the speed at which information is carried. If you are more interested into knowing this, you can just check the Wikipedia page of basically the group velocity and the phase velocity because we are running out of time. So if you are interested in knowing what basically a phase velocity and group velocity of a wave are, you can go to a Wikipedia page and you can understand it clearly. A lossless transmission line has length 2 meters, phase constant of 8 pi by 8 radian per meter, characteristic impedance, load impedance. We need to find the reflection coefficient. Okay, reflection coefficient uh, we know that it is ZL minus Z0 divided by ZL plus Z0. What is ZL and other things? These are basically associated with the characteristic impedance is given, the load impedance is given. So this is characteristic impedance Z0, this is load impedance ZL. So you have 150 minus 50 over 150 plus 50. So this is basically 100 over 200. So this is 1 over 2. So this is 0.5. So the 0.5 is basically the reflection coefficient. That means 50% of the wave is going to get reflected. Okay, so from the data in question 6, input impedance is, we need to find the input impedance. And there is basically a relation between input impedance and the characteristic impedance and load impedance, which is basically something like ZL plus J times Z0 tan of beta L divided by Z0 plus J times ZL tan of beta L. So everything is, I guess, given. You have a length of 2 meters, which is L. You have given a phase constant, which is pi by 8. This is also given. So you can just put these values here and you are going to obtain this Z input impedance. Characteristic impedance is also given. ZL is also given. This is just a straightforward problem. You're going to get 30 minus 40J, which is basically 30 minus J40, which is basically this particular thing. So this is the real part. This is the imaginary part. Okay, so most of the times it's basically written as R plus JXL. This something like this. This is basically the reactance part. So this is the resistance, this is the reactance. It can be inductance, it can be capacitance, depends upon XL and or XC. Then this is the overall impedance. Okay. From the data in question 6, the VSWR, which is the voltage standing wave ratio, it denotes that where does the basically the maximum of voltage occur in a transmission line. Okay, and it's very important quantity in the microwaves as well. And this VSWR is basically given as the dependent upon the reflection coefficient. It's given as 1 minus the reflection coefficient divided by magnitude. It's basically the magnitude here divided by 1 plus magnitude of reflection coefficient. And because you have found the reflection coefficient, that was 0.5, so you can write it as 1 minus 0.5, 1 plus 0.5. So you have 0.5 over 1.5. This is basically 5 over 15, which is 1 by 3. Okay. Did I messed up? Okay, I guess this is plus, this is plus, this is minus. So this should be 1 plus zero point 0.5, 1 minus zero point 0.5. So this is basically 5 over, this is 15 over 5. So this is 3. So this is exactly 3, the voltage standing wave ratio. And we need a capacitance from a lossless transmission line with phase constant this, characteristic impedance this, and ZL equals to 0. The length of the transmission line is. So since what is basically happening is ZL equals to 0 is means that this is a short circuit at the load. Okay, that means it's a transmission line with something like this. So this is the input side. This is the input side. This is the output side. There is a short. That means ZL equals to 0. Okay, and the Z input is basically J times Z0 tan of beta L. These are the relations basically derived. Okay, and what else is given? This is basically equivalent to minus J times Z0. And it turns out to be that you can write L equivalent to tan inverse of minus 1, which is basically which is basically 3 pi by 4, or it's approximately 2.35. So this is exactly 2.35. Okay, so this is the length scale of the transmission line, which can be obtained from the relation simply, or even you can use let's say this particular relation. This is the exact relation we used, but because ZL equals to 0, so you have Z in to be only equivalent to J times Z0 tan of beta L. That's as simple as that. Okay. And now the final question is that open circuited lossless transmission line has open circuit means ZL is infinity. That means this is open at this end. So ZL is infinity. And if ZL is infinity, that means the reflection will be 1, because whatever the electromagnetic wave will come, it's going to entirely reflect because it will not go to the load. There is no load. Okay, it's open. So it will entirely reflect. And VSWR, which is basically S, is going to be infinite. Okay. If this, I don't know if this S, no, I don't think if this S represents VSWR here. Need to check. Okay, but the answer of this question is that ZL should be infinite. The gamma should be 1, which is basically this particular option, that the reflection coefficient is exactly 1. Let's see if this makes sense. Yeah, so if this VSWR is 1 plus gamma L divided by 1 minus gamma L, so if this is 1, so it will be 1 plus 1 divided by 1 minus 1, so this will become infinite. So yes, this is S is basically the VSWR, standing wave ratio. Okay, that's the end of this particular problem set, which was basically given. And this is, we're coming to the end of this session. Mostly, I guess this was a super fast session, but I'll try to keep it slow in the next sessions. But this happens usually in the first session and usually because you have to cover the entire week. So it's not possible always to uh, cover certain things or go slow, because these videos are available on the YouTube and you can just watch them anytime. If you have any doubt regarding any questions, you can ask them in this session, or you can just email to the NPTEL coordinators. We are here always to just answer any of the queries. But my job here is basically to give you a different flavor of this particular course in terms of the applications, in terms of the directions, research, open problems right now, which are basically in this course. So that's it from my side, basically. If you have any questions, you can just ask me. Otherwise, I'm going to basically stop this particular session. Thank you.